team of scientists and special effects experts are coming together to build the world's biggest ever model volcano.
This is huge and heavy. It's a really big project.
When I say on the edge, I mean on the edge.
In the search for knowledge, the team will face extreme environments.
It's amazing how just one glimpse at that glowing red stuff can just like get going.
Huge engineering headaches.
How's your heart rate? I need to lie down.
Major scientific problems.
My heart sank to my boots at that moment, actually.
And will create quite a mess.
Well, that was a little dusty. 3, 2, 1. Fire in the hole!
In an abandoned quarry, something big is underway.
Measure this out. 32.5. Hey, Ben. Yeah. Gotta go towards you. Oh, right there. Oh. That corner has to touch this edge. That's where we want to be. When I say on the edge, I mean on the edge.
This is the first stage of a giant model volcano. The idea of a group of scientists who dream of doing something that's impossible at a real volcano. Seeing inside an eruption.
At a real volcano, all we can see is what's going on at the surface.
But we need to know what's going on inside if we want to make serious predictions about the hazard they pose. And so this experiment allows us to get inside. It's big.
We'll be able to see everything that's going on throughout the entire system.
The plan is simple. Build a model designed to mimic the two very different ways that real volcanoes erupt. First, the scientists want to recreate what happens when molten rock turns into hot ash as it erupts, devastating the surrounding terrain. Then, they plan to look deep inside a volcano and replicate the conditions that force out rivers of liquid lava. And they want their model to be massive.
It's important to do very large-scale experiments because systems behave differently depending on what scale you look at.
It may not work. It could be a huge catastrophe. Everything could collapse. The whole volcano could implode and blow up. I hope not.
Well, bigger the better.
The scientists have wanted to do this for years, but the problem is, they're academics, not engineers. So to make their dream a reality, they get help from a special effects expert, Max McDonald, a man with a reputation for being able to build and then explode just about anything.
Digging out lots of houses, blowing cars up in the air, flipped them over. Not that exciting anymore, but still better than selling pencils, I guess. Watch your head!
Taking time out from the day job, Max has agreed to give the scientists 2 weeks, and he's getting straight to work.
Put the cherry on top, so 2 guys get up there and we position that dead center.
From tough reinforced shipping containers, Max's build team have created a skeleton for the model, over which they'll build a 4-story high, 45-meter long volcano flank. If the model volcano is going to help the scientists answer volcanology's big questions, it can't just look like the real deal. It needs to behave like a real volcano too. And in preparation for the first eruption, Michael Manga, accompanied by local volcanologist Brittany Brown, is on a fact-finding mission to America's most infamous real volcano, Mount St. Helens. The scene of an eruption in May 1980 that tore this mountain in half.
The Mount St. Helens eruption in 1980 started with a massive landslide, the largest landslide in recorded history. 1,300 vertical feet were taken off the mountain and slid down the valley.
In seconds, the landslide destroyed the mountain's north face, releasing thermal energy 1,600 times greater than that of the atomic bomb dropped on Hiroshima. But what happens next is far worse.
Within seconds, the lateral blast was shot out of the volcano. The magma that was pressurized exploded laterally out like a shotgun.
Millions of tons of pulverized lava, in the form of ash and gas as hot as 1,000 degrees Celsius, spews out. Much of this ash rose vertically in a column, but some parts then collapsed, forming devastating currents of debris that moved down the mountain at over 1,000 kilometers an hour.
So where we're standing here, 12 miles from the volcano, what we would have seen is this ground-hugging cloud of searing hot gas, ash, and rocks coming up and over this topography at us at incredible speeds. We would have maybe had less than a minute to stand here and watch it, and there was nothing we could have done.
These currents, known as pyroclastic flow, are the most deadly and unpredictable force in a volcano's arsenal. And scientists have many questions about them.
What controls how those flows behave? What controls how fast they go, how thick they go?
One of the big challenges with understanding real pyroclastic flows is that we can't get inside of them.
Now, the team wants to find some answers.
One of the goals of our experiments, in fact, is to try and understand how these pyroclastic flows interact with ridges, bumps, mountains, to either keep going, mix with air, or take off vertically.
Back at the build site, the plan is to test how ash currents react to terrain, so the team need to create a mountain flank, complete with ridges and valleys, similar to that at Mount St. Helens. So volcanologists Ben Andrews and Joseph DeVec are working with one of Max's team, feature film production designer Andy Berry.
This is huge and heavy. It's a really big project. I have nothing really to compare it to.
To recreate Mount St. Helens pre-1980, the team need a steep upper slope and a huge sweeping lower flank, down which the current will flow. Andy's team are creating the upper flank, the good old-fashioned Hollywood way, starting with a wooden frame, some chicken wire and some burlap sacking, topped off by quick-dry plaster for a stiff, lifelike finish. While the lower slope gets shaped from 400 tons of soil and rocks that happen to be lying around at the quarry, just what the scientists need.
We can get it to collapse in the chute, we'll have it come down, and then with shovels, we can probably just sculpt our own channels coming out here onto the plane.
Next, it's time to break out some slightly less high-tech tools for the painful process of sculpting the ridges, valleys, and other mountain terrain. A job no one wants.
So that's how you do it. I'll be back in an hour.
With the volcano taking shape, it's time for Ben and Joseph to start playing with dust, or rather working on the simulated volcanic ash. And to make sure it's right, Michael Manga has returned from Mount St. Helens with a bag full of the real stuff.
So we can see here the grain size distribution in the natural pyroclastic flow has very fine grain ash as well as very coarse material.
At Mount St. Helens, most of the ash was light enough to rise as a huge vertical column, but some denser sections collapsed to roll down the mountain. To reproduce it, Ben and Joe tried different mixtures. A buoyant industrial ash known as fly ash and some sand gives them density.
3, 4...
They then test the mixtures by doing what volcanoes do to ash, they heat it.
Much hotter. That's good. Actually, quite hot.
Perfect. A buoyant column with some parts dense enough to collapse.
So if we can now replicate this on the big mountain with a higher mass flow and the same temperature and mix of particles, we should get these currents that'll now go down the hill and should lift off just past the change in slope.
That's right.
Now they've got their mix right. All they need is a way to make it erupt. When building a massive model volcano, how do you get it to erupt? Max has a simple yet effective plan. He's going to make cannons using steel pipes and blast the ash out using compressed air.
Here's one with a nipple. We'll put a valve on it, that kind of thing. So basically this is fluid analog, and we introduce whatever pressure air you want. If it's kind of low pressure, it will sustain it for a while, quite a while. And if you want it to just bang out and collapse, this will do it.
And to give the eruption an initial boost,
You hit it. Don't worry about the motor.
explosives, courtesy of Max.
This is a fairly small charge, but appreciate that it's going to be bigger than this, okay? Okay, Ben, I'm going to say go hot, and I'm going to go 3, 2, 1. You hit it on 1. 3, 2, 1.
It looks as though the team have found the perfect way to make their volcano erupt, but success on the day is not yet guaranteed. To create a successful debris current, the ash will need to erupt, fall and flow in precisely the right direction down the flank, and that is harder than it sounds.
Okay, Paul, you go get a ball valve. Hit it. Okay, leave it on. Well, that was a little dusty. I think we ought to be upwind from that from now on. That's pretty funny, Ben.
It becomes clear that there's one factor that threatens to ruin everything. The ever-changing weather. The team don't have time to wait for perfect conditions, so it's time to cross their fingers because tomorrow, rain or shine, this volcano is set to blow. On site, the build team struggle to fit the cannons into place. The science team, meanwhile, have decided to spice up their volcanic ash mixture with some colourful everyday items, including ping pong balls and peas.
This is our last bag of peas, guys. What we'd like to do is put in something that we can use as a tracer inside the volcano. So our hope is if we color some pink, some green, and some orange and put them in different places, we can keep track of them as they move through the volcano.
Oh, if the can is more upright, show us your table tennis skills. These guys here should be pretty good because unlike a grain of sand or the fly ash, these will bounce.
Hopefully we'll be able to pick this up with the cameras too, and we
These
can
are
track
big
their
enough.
location up here.
Next, the guys put their monitoring equipment into place. The thermal and wide-angled mini-cams could never survive a flow of real super hot ash, and neither would these glass sample slides.
You want me to hold it?
Something we don't normally get to do, we get to sample the inside of the flow with this sticky tape.
Meanwhile, Ben is up top.
You could have a half pail of sand in each one and start heating it. If we dump all the sand in at once, we won't be able to heat it very well.
He's making sure the mix of material is loaded and heated correctly.
That's good enough on the heat. I think we can start adding the fly ash into the tubes. Want a mix of about 3 to 1. Some peas and some ping pong balls. We can start sprinkling those in right now. Yep. We want to get as many of things mixed together. Looks good. All right.
Now they need to erupt the volcano while the ash is still warm. But first, the volcano needs a name.
It's a bit like Mount Doom over there, so we could go from Mount Boom.
I like Mount Boom.
Mount Boom. You get a big enough eruption at the top. Yeah. Mount Boom.
Mount Boom.
The newly christened Mount Boom could help answer a big question. For years, scientists have theorized that debris pyroclastic flows moves across terrain in one direction, like water in a river. That's why they call it a flow. But does this theory stand up? It's time to find out. But only if the erupting ash column can collapse and flow onto the mountain flank as planned.
Let's go! Showtime! See you on the other side.
So while Joe and Michael man the monitoring equipment, the rest of the team take front row seats for the most ambitious volcanic experiment in scientific history.
Think we're safe here?
Do you think? Yeah. Do you
I'm
think?
gonna say, you're the bravest people I've ever met in my life. Should be okay. What can happen?
The only thing that next FX guy you always say.
That's it. The only, okay, the most dangerous thing is something flying, so keep your eyes peeled.
Okay.
Let's go! Stand by! 3, 2, 1, hit it!
It's an eruption, but not quite what they had hoped for.
We can definitely see what happens when you have a strong wind. That was a good shock. I mean, looks like you blew a hole in the entrance there.
Yeah, I felt it.
Yeah, if we didn't have this wind, you would have got a nice plume. Coolio!
Slow motion cameras reveal that the violent eruption blasts an ash column over 20 meters in the air, meaning Mount Boom erupted just like a real volcano. That's the good news. The bad news is that just at the last moment, the wind picked up and blew the ash in completely the wrong direction, failing to form a current rolling down the mountain flank that the science team had hoped to study. The science team now has a problem. They only have Max for another 5 days, and this is only the first of 2 major experiments, so time is running out. If the next attempt isn't a success, they will have to abandon this experiment and move on. Dawn at Mount Boom, the biggest model volcano ever built. The team is about to erupt a column of ash they hope will collapse and create a current that they can study as it flows down their mountain flank. Now they need the wind to act in their favor and take the ash in the direction they need.
It's a bit windy. It's about 2.5 meters per second right now. Anytime they're ready.
Well, let me get ready.
So,
Stand by! Hit it!
Wow.
there's some waves on the side.
It's collapsing now. We got it. Collapsing.
Look at it go.
Here we go.
Keep going. We definitely have a gravity.
That's a very nice current. And look at how that's going to go right over the gap.
Right over the top.
Oh, that's beautiful.
To the naked eye, the eruption seems to have worked. But is it a success scientifically?
What's it look like?
You can see the density gradient. It's really
They
great.
check where the flow is deposited.
Oh, look, wait, here's a ping pong ball.
BP there.
Look at this. Wow.
Yeah, we had a very impressive gravity current, a very nice column. So I think that was a lot of fun. That was better than I was expecting it would be.
Then they begin to analyze data from the monitoring equipment.
Look at that eruption column go. That looks like a regular eruption.
The results are surprising.
So it's erupting at 20 degrees. It's all uniform temperature.
They went high.
Very, very high, very high.
Obviously stuff is moving. Big things are moving here. So that's really amazing.
Volcanologists have always thought that pyroclastic flows were relatively simple currents. But the results from the slides and the sticky tape all over the terrain suggest otherwise.
When the flow was going down the little channels that were carved into the hill slope, we got to see the pyroclastic flow spill out over the edge. And there's a huge amount of material deposited right on the edge of these channels. So there was a different type of interaction with topography that we got the chance to study.
Being able to see these denser sections of the flow was amazing.
Volcanologists have always assumed pyroclastic flows moved in the same direction across terrain like a river. But here, the ping pong balls and coloured peas moved sideways, backwards, all over the place, meaning there is greater turbulence inside pyroclastic flow than anyone realised. This all means that Mount Boone's first big test has been a success, and the scientists will go away with yet more questions to answer, which apparently is how they like it.
Ran the experiments and they surprised us, and that's always what you find. And you take that surprise and you turn it into a new set of questions.
I view this sort of as a starting point for thinking about how to do bigger and better experiments.
Encouraged by their success, the team is moving on to the second and even more ambitious experiment. This one aims to replicate what happens deep inside volcanoes and will answer the biggest question of all: what causes a volcano to erupt in the first place? The generally accepted theory is that at the heart of all eruptions is something you might find surprising: bubbles. Just like a carbonated drink fizzes from a freshly opened bottle, it's thought that gas bubbles form deep under a volcano, causing the molten rock known as magma to rise in just the same way. But exactly how this happens, no one's sure. That is what the team wants to explore. So to find out more about the role of these volcanic bubbles, Ed Llewellyn and Jeff Johnson have come to a real volcano called Stromboli off the west coast of Italy. Dozens of times a day, Stromboli erupts at a low level, making it the perfect place to study eruptions. Ed and Jeff have joined a group of Italian volcanologists, making the steep 3-hour hike to the summit.
See those layers up there, Ed? Those are beautiful. I love stratovolcanoes.
It's a walk in the park for field specialist Jeff, but slightly tougher going for Ed.
My pack's about half the weight of yours.
You know what I have in here? Bubble wrap.
So exciting.
2 hours later, the group approaches the crater, where visibility is near zero.
Hear that?
Gas jetting.
Yeah.
Cool.
All around them there's a foul-smelling, throat-burning gas, sulfur dioxide.
I don't envy the dog with his sense of smell in this.
And they can hear jets of another gas being released. This is steam, the gas they think creates volcanic bubbles. And as these bubbles burst at the surface, they throw up chunks of molten rock known as scoria.
I'd feel a lot happier if I could see that.
team sets up an array of equipment to measure everything from temperature and gas levels to the sounds the volcano makes. In Italy, the fog finally clears enough at Stromboli for a few small glimpses of volcanic activity to be seen.
It's amazing how just one glimpse at that glowing red stuff can just like get you going, huh? It's exciting. I want it to clear up just one more time. Gotta see something down below.
But as they see more, it soon becomes apparent that the normally predictable Stromboli is behaving unpredictably.
We're all buzzing actually. What we're actually seeing is something quite unusual.
Usually, Stromboli just belches gas and small amounts of lava. Today, the volcano is pumping out huge flowing rivers of the stuff.
That's something that's real special. We don't often see lava flows within the crater area of Stromboli, so this is a privilege to be up here today.
For volcanologists like Ed and Jeff, nothing is more exciting than seeing a volcano doing something new. But this could be deadly. Sometimes these lava flows are a signal that the mountain is ready for a massive eruption.
Anytime there's a change in activity at a volcano, it's a warning sign. The last couple of times that's happened, the magma level was unusually high, and there was lava eruption on the crater terrace, and these preceded the largest explosive eruptions that you get at Stromboli, and these can be very hazardous.
Ed and Jeff's Italian guides decide it's too dangerous to stay on the mountain, but their equipment remains, collecting enough data to feed back to the Mount Boone site over 8,000 kilometers away, where the team is gearing up for another, even more ambitious eruption. A few days later, the team runs through the plan to simulate how they think the bubbles cause volcanoes to erupt molten lava.
That'll govern how high the eruption column goes. If you want to get 35 meters, you need lots and lots of bubbles.
The theory is that as magma rises from the vast chambers within the volcano, it reacts to the changing pressures by allowing gas trapped within to escape and form bubbles. The behavior of these bubbles then creates many different types of eruption. From the large single bubbles that fuel Stromboli's little belches, to the mass turbulence of lava flows, exactly what the team wants to recreate.
We need to understand how those gases dissolve in magmas, how quickly bubbles can grow, how quickly the magma can rise.
The scientists' ambitious idea is to build their own magma-filled chamber, connected to a volcanic chimney. The trick here will be to create constant high pressure in their model chamber, like the real thing. The scientists, though, think they have a solution for that too. A huge weight of liquid pushing down a 12-meter pipe, supported by a reserve supply of liquid in something they call the header tank. It sounds simple on paper, but Max is worried that what the science team want won't work in reality.
What works in the lab under control conditions doesn't necessarily work out here. We wouldn't do a build like this. We'd, of course, give her the header tank. We'd feed in pressure from the bottom, but that's not what he wants. Let's go look down here and see what we can find.
Max reluctantly agrees to give the idea a try, but first he needs to find some raw materials. In this old boiler, Max thinks he's found the perfect centerpiece for the experiment. A chamber that will be filled with high-pressure simulated magma, and then pumped with gas to create bubbles. But can this magma chamber really withstand the pressure created by over 7,000 kilograms of liquid?
It doesn't hold the pressure. The whole experiment is kaput. We'll have to get one to the shop, see if we have any leaks anywhere, and see if we have any bulges. If it works, great. If it doesn't work, we'll go down a different route. But we got to do it quick.
With only 3 days of his time left, Max wants to hurry the build along. Ed, though, insists that things have to be done exactly right.
We could come out here and have some fun and build a big volcano, but I want to do some science as well. That's really important to me. There's some important questions that we can answer using this piece of kit, if it's built properly.
Over the next 48 hours, they rush to get building, turning a bunch of scrap metal parts into a potential volcanic system.
The setup's really very simple. Actually making that happen is really very difficult.
Okay, so take her all the way to the top and be careful.
Max has picked up another steel drum to be the header tank. And now, after the first 7-meter section of downpipe has gone in, it's time for the moment he has feared, fitting the header tank into position at the top of the volcano.
We're going to take a header tank, we're going to see how stable it's going to be and what we need to do to stabilize it.
But as Max and his team try to position the tank, they can see Ed's plan has a flaw. The tank will be unstable.
The engineering challenge just of supporting a header tank that's 40 feet up in the air, that's difficult, and you've got to get it just right because otherwise it's not safe.
In effect, we do a lot of things on the edge, as far as, making it look great and everything else. But when it comes to structure, we don't do anything on the edge. If you're on the ground, that's one thing. We're up 4.5 stories high. Gravity's not going to be forgiving at all. We're not there. And we have to rethink how to get there.
Max goes back to the drawing board. Meanwhile, the rest of the build team is busy making a magma chamber. But how are the scientists going to recreate magma itself? To find out, it's time for a few tests on a smaller version of the pressurized chamber.
1.2 bars. Wow!
Magma is a liquid, it's molten rock, and it's got gas dissolved in it, in just the same way that a soft drink is a liquid with gas dissolved in it.
Scientists believe eruptions are caused by the simple action of bubbles rising through liquid. So after testing out a few familiar liquids, such as ketchup and beer, they've decided to replace real molten rock with a low-tech substance, water.
Only at about 0.2 bars. Well, we have beautiful bubble plugs.
So, they have a magma chamber, and they have magma. What they need now is a way to create really big bubbles, or slugs, as scientists like to call them.
Right? Hugo and his guys have built a gas trap. It's basically just an inverted pipe that's got a trapdoor on the top. So we can bubble gas up from underneath, and we need the lid, the trapdoor, to be able to hold the pressure of the gas inside that pipe. I want to check the seal.
There's a couple bubbles out
So let's just see if we can get that seal just a little bit tighter. This is our last opportunity to get back into the tank if there's anything wrong. Once it's sealed, we can't get back in there.
There you go.
It's full.
Got him!
Well, it works.
It works.
That was fantastic. Let me know when you're going to pop the lid next time.
Sorry.
The magma chamber is ready, but now the rest of the pipe system needs to be fitted, and that means figuring out how to get the header tank filled with 1,500 kilograms of water to balance on this pipe. Luckily, Max has a brainwave that might just save the day. At Mount Boom, construction is underway on the inner workings of the volcano, and Build Chief Max McDonald is about to introduce some heavy metal.
What I'm thinking is we make a huge header tank, but it's self-supporting.
Instead of trying to make a large tank balance on a 25 centimeter diameter pipe 4 stories up, Max plans to replace the whole thing with one huge self-supporting pipe. A 1 meter wide, 7 meter long, 3-ton steel beast that will be safe and give the team a sufficient volume of water to provide constant high pressure to the magma chamber. Bringing in a huge crane to load it into place, the monster pipe sits beautifully on a custom-made plate.
She's looking good. Hey, Ben! Is it lining up? Perfect! Excellent! If that was a 1/4 inch, 1/2 inch out, any of the bolts, it wouldn't fit.
It's time for the final piece of the jigsaw. The 12-meter long, transparent volcanic chimney rising vertically from the magma chamber. As it starts to get dark, the clear chimney sections finally go in.
Very nervous.
Hugo, before it goes any further, can we get a rag or something over that I-beam? Because I think the metal would be able to scratch the legs out. Okay, great, thanks.
If it doesn't sit perfectly in place, the experiment might not work.
Good enough.
Good enough?
Yeah.
So we'll just try to get those collars on so we'll be ready by morning.
How's your heart rate?
That's good.
I need to lie down.
The next morning, the countdown to Mount Boom's second eruption has begun.
It's been really exciting. I've been thinking about building some experiments at this scale for a couple of years, and it's really amazing to actually see it finally coming together. But there are a couple of things that are really challenging.
Be real careful there.
One is going to be making sure everything's sealed and able to withstand the pressures. So it'll be interesting to see when we load it with water whether or not it actually starts leaking everywhere.
Perfect.
The team are preparing to fill the apparatus with water, coloured to make observation easier. But will it hold the over 7,000 kilos of weight?
We've put some indicators on the bottom. If you guys start hearing something, like that means there's movement when we start filling the header tank, because that's a lot of water and that's a lot of weight.
So Max, I'm ready when you are to start filling. We'll take it slowly, okay? So that we can check for leaks.
The system slowly fills. It's not the 100% leak-free pressure-tight system the team had hoped for, but they feel the experiment is ready to begin.
Can we ready to send a couple of slugs up?
First, the science team wants to test the theory that belches of lava like this are driven by the behavior of large single gas bubbles like this.
We really don't know. We are testing a hypothesis. That's what scientists do. The hypothesis is that you can form a gas slug in a conduit. We're about to test that hypothesis.
If they can form one long, slow slug of a bubble, they'll have shown the theory is correct.
Ready? 3, 2, 1.
Something has gone wrong. Lots of small bubbles are causing the big slug to break up.
It's a slug, but it's too short.
This can only mean that there is a problem inside the chamber.
That vent seems to have moved at the bottom. It's not just bubbling up into the slug trap anymore.
The slug trap isn't doing its job, and gas is escaping.
It's coming up.
mainly around the sides.
Oh, yeah. Yeah, well, that's not good.
My heart sank to my boots at that moment, actually. I thought at that point we probably weren't going to be able to do any useful science.
Inside the fully sealed magma chamber, this is the worst place for a problem. But for Max, failure is not an option. It's time for some drastic measures. Open heart surgery on the faulty magma chamber.
Go eyeball that, see what you think. Ah, watch it. Oh, right outside, right?
Yeah.
Yeah, well, that's the problem. It's popped right out.
If they can fix the leak around the top of the gas trap, then I think it'll be fine.
And if it doesn't work this time?
I don't know.
Everyone's hoping they fix the seal on the gas trap. The system is refilled with water, and it's time for take 2. Can the team demonstrate for the first time what might be going on inside a real volcano? Scientists at Mount Boom are about to find out if it's possible to create the huge gas bubbles they believe are responsible for the belches of lava seen at many real volcanoes. After months of preparation and weeks of building, this is the moment of truth.
Okay, I'm going to try letting one go. Ready? 5, 4, 3, 2, 1. There we go, we have liftoff. A little bigger. We have a slug! You did it! Got a slug? Perfect slug!
Nice work.
Good work. When we popped it, slug went in. Beautiful, smooth cap on top of it. Just what we're hoping to see.
It may only look like big bubbles in a pipe, but what the scientists are seeing here for the first time is that gas slugs can form large enough to drive activity at volcanoes where lava erupts in belches.
This is a really cool experiment. I think we are seeing what may very well happen in volcanic eruptions, where we have large slugs of gas that are coming up the magma conduit and explode out the top.
When you're working on a volcano, you can only see what's going on at the surface. And what we've been able to do here is to look inside the volcano.
We've speculated that this sort of phenomena occurs, and now we've been able to observe it firsthand. And it's a very exciting observation for us.
Do this exact one more time.
So the biggest one, do twice.
Yes.
That's our most precise measurement, and we can see if we can replicate it.
That's right. I wish I'd thought of that, but yes.
So far, so good. Bubble behavior can, it seems, explain short belches of lava. But can it also explain eruptions that spew huge, sustained lava flows? To find out, in Mount Boom's final and most explosive experiment, the science team will flood the chamber with as much gas as possible. Music to Max's ears.
And when you say as much air, we're just going to go through the little air coil, or do you want to put 1.5 inches in there?
I want to put the most gas we can possibly get through there.
Let's run from the compressor 1.5 inches, put the 100-footer, put it in the bottom.
You put it in through the water. Is that we're going to put in? That's what we want. Yeah, as much gas as we can get through there.
The theory is that sustained lava flows occur when the bubbles just keep coming. These rise at first as high-speed slugs. When they reach the surface, they explode, clearing any blockages. Now the magma flows become fast and turbulent, breaking up the slugs and driving massive quantities of magma out of the volcano. But can the team create this effect?
Okay, we're pressured up. You say when.
Okay, Hugo. When you're ready.
See you on the other side.
The countdown begins.
And stand back. Ben's ready to get behind that container. Yeah? If anything goes wrong, run.
They're about to get slightly more than they bargained for.
eruption. Good job, guys.
Mount Boom has taken on a life of its own.
That's how a volcano erupts.
And thanks to Max's enthusiastic gas injection, its power surprises everyone.
We popped off that plug just like a volcanic eruption.
We did. Great. Yeah. There was so much pressure went into the magma chamber that it went up the YouTube.
You gotta be careful when you tell me lots. Because lots to you and lots to me is different.
Once again, the team has replicated conditions they believe exist in real volcanoes, showing the crucial role that gas bubbles play in lava flows.
We've been able to look at the dynamics that go on inside the magmatic plumbing system, and that's absolutely critical.
It's the perfect finale to an incredible series of experiments at Mount Boom, the largest model volcano ever built. From the high-pressure world of bubbling magma, kilometers beneath the Earth's surface, to the devastating ash currents that can engulf whole mountains and communities, the Mount Boom team has been able to see inside mysterious volcanic processes, shedding light on some of the world's most dangerous and unpredictable natural phenomena, taking them one step closer to volcanology's ultimate goal.
Volcanoes kill people, and they destroy livelihoods and they destroy homes, and that's ultimately why we do what we do, and everything we learn about volcanoes helps us to do that job better.